Hi, Umbra. How's it going? Chat, is this real? I know, right? I never stream. Who am I? Who is this guy? Who is this guy, chat? Who stole my streamer? Who doesn't stream? Here's my... Where my thing is. I renamed my file directory, so if anything breaks and it can't find anything, we're gonna find that out. Oh, this might break too, actually. Oh, yep. Yeah. Okay, let me find this. I renamed a lot of things, and there we go. We're gonna do linear. We're gonna tackle the ones that I just straight up couldn't do, which is awesome. Which is the what are they called? The residual ones, which I can't believe I remember that name, but anyone who was here, data analysis, we hate that class, but it's okay. I remember one thing from it. Residuals are a word that is in that. Turn down the music just a skosh. Love Katamari. Okay, we're gonna vibe out. We're either gonna vibe out or it goes badly and then I switch to Doom soundtrack, okay? That's what's gonna happen. Alright, we have to find the least squares best fit line for the data, some data that he gave us. These are eerily similar to the ones that he gave us before, but it's fine. -4, -1, -3, 0, -2, 1. Oh, it's gonna be a 5D matrix. No, oh, please. Okay, it's fine. Alright, so -4, 1, -3, 0, -2, 1, 0, 3, 0, 7. So our general equation for a line is going to be y equals mx plus b. So I'm just going to go ahead and we're going to set up a. So essentially we want to plug all these points into this equation and get a system of equations. So it's a very over-constrained system, obviously. A line can be made by 2 points. We have 5. Not going to make a good line, but we can find a line that's kind of there if we project onto a space. So we're gonna have all of the x ones here. So it'll be -4, -3, -2, 0, 0. That's nice. And then we have a bunch of ones because we're gonna factor out. Well, we're not gonna factor out, but we're gonna multiply this matrix by MB, because those are our variables we want. And then that's gonna equal, well, I mean, it's not gonna equal anything. Yeah. I'll do this. So this is like A, like V, or no, here, AMB equals Y. And this will equal all our y values. -1, 0, 1, 3, 7. So here's our system of equations that we would want to solve. You know, you would set this up so you could row reduce it or whatever, but we can't do that because it doesn't exist. So that's great. We love that. But we're going to project y. So we need the projection of y onto S. Now we could use, like, you know, whatever. We could use an orthogonal basis. We could Gram-Schmidt orthogonalize. Or we could be smart and we could do the normal equation. So the normal equation, we're gonna say normal equation. So I remember that that's what I'm doing. I believe it is this. It's A transpose A inverse times A transpose Y equals I mean, in our case, MB. Now, is that true? Let me think about this. Does it equal MB? Yes, it does equal MB. Except that... it's a linear combination of the columns of A. Is that gonna actually give us MB, or is that gonna give us a funky little thing? I should check that. Because when you play around with bases, sometimes you get results you're not prepared for. So let's do a check. That is, it's gonna be like a linear combination of the columns of A and B. Linear combination of the columns of A for sure. But is that? Oh yeah, that would be right, because we have like a certain amount of X and then a certain amount of B, and the certain amount of B, like B is 1, so then that'll be M times something plus B essentially. Cool. Okay, we need to do A transpose A. Who's ready for 5 by 2 times 5 by 2? Well, it's 2 by 5. I think I did this last stream, but I'm gonna do it again. One cool little thing my professor was doing was he would write the transposes like this, so that you could just FOIL them out instead of having to think about it. So if we do this, this is gonna give us a 2 by 2. So we do this one with this one, this one with this one, this one with this one, and this one with this one. Is it actually going to give us a symmetric matrix too? So it's like first, outer, inner, whatever, last, I don't remember how FOIL works. Okay, so it's going to be 16. Alright, 16 plus 9 minus 4. 16 plus 9 is 25, minus 4 is 21. Minus 4, minus 3, plus 2. Minus 4, minus 3 is minus 7, plus 2 is minus 5. This one's also going to be minus 5, and then we just have 5. And that's really nice because it's 2 by 2, our inverse is going to be clean to do. I'm not going to invert it first, I'm going to do the A transpose Y. Because, you know, I'm cool like that. I don't want to do the inverse. Oh wait, this is a -2. That changes everything. What is that? So it's 25 plus 4, 29. And then this is going to be -4, -7, minus 2 is -9. Doesn't change everything, but it changes those. Okay. You know, be meticulous, be meticulous. That is not me at all, unfortunately. Don't know why I'm an engineer. That's fine. And then Y is -10137, and let's just check that that's right. -10137. Beautiful. So we're gonna get a 2 by 2 here. It'll be, and then it goes like first, last, like that. Alright, so 4, 0, minus 2. 4 minus 2 is 2. Okay, that was easy. And then we just add all these up. So 1 minus 1, or yeah, 1 minus 1 is 0, so this is 10. Oh, thank God it was easy. Okay. Look at that, 2, 10, that's a pretty nice number. Okay, now we have to do A transpose A inverse, which, you know, isn't actually that bad. So we do the determinant first, so 29 times 5 minus 81. 29 times 5 minus 81. 64. And then we flip these two, and we flip the signs of these two. Like that, baby. And then we just have to multiply this and that together. That's, pretty chill. A transpose A inverse times A transpose Y equals 1/64, 5, 9, 9, 29, and I don't have a fun way of doing this one. It's gonna be 1/64. This and this Okay, so 5 times 2 is 10, plus 9 times 10, that'll be 100. And then... my entire brain just stopped working. 9 times 2 is 18. 18 plus 290 is 308? 308. I think we can pull out some stuff. Let's see. So if we do a 2, it'll be 1 over 32, 50, and 308, 154? Can I divide this by 2 again? I can. 1 over 16, 25, and let's see, 50 plus 25, 75, 77? I think we've exhausted our stuff. But we can check, so let's see. If I was gonna plot these points just really roughly. Those are top. There's a 7 in there. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Don't worry about the scale. 1, 2, 3, 4, 5. 1, 2. Fuck, that was... okay. 1, 2, 3, 4, 5, 6, 7. Okay. We have -4, 1. There. We had -3, 0. There. We had -2, 1. There. 0, 3. There. And then 0, 7. Oh, I see. So, like, that, sort of. Maybe a little bit more like that. But it's positive, and there might be a B value. Let's see. I drew it through the origin. It probably doesn't go through the origin. Let's check Desmos. Nice, because it's gonna be like roughly correct, but it might not be exactly correct. But it is a good idea to know how to do this. So -3. Oh, let's go over to Beautiful World. I think it's gonna be showing me. Oh, it's not showing me. Look at me. I was a good boy, and I actually turned off things. Okay, -3, 0, and we had -2, 1, and then we had 0, 3, and then we had 0, 7. Oh wait, 0, 7, I'm stupid. It's not an X value. Get out of here. I'm gonna change that. Okay, that makes a lot more sense why there would be an intercept that's high. Okay, good. That's why we check things. Okay, oh. I forgot my keyboard doesn't have a tilde on it. Oh wait, this one does. Oops, A, X, sub 1, plus B. Let's see, so 1.5, okay, we had 100 over something. We had 25 over 16. A, that's right, that's right. And then we had 77 divided by 16. Let's go, it's exactly the same. That's awesome. That's really awesome. Literally the exact same line. That's awesome. Look at that, we made that chat. This is us. We did this. We did this. It was so easy. Like, I mean, and even more realistically, like, if you were trying to do this, like, in MATLAB or something, it would be so easy. Turn that off just in case. Why is it switch me to my... Okay, sure. I don't know why W switches my screens, but it does, I guess. Did I set up a key to do that? Maybe I did. Maybe I forgot, and I did. Yeah, so it says... find the least squares best fit line for the data. Oh. The second one is a matrix. I just, like, didn't read... not a matrix, a parabola. Because I was, like, reading it, and I was like... Or in class, he said, like... Oh yeah, number 4 is a parabola, and I was like, he doesn't even know what problem he's talking about. Number 4 is not a parabola. I didn't know what problem I was talking about. Suppose you have a data set consisting of the points 2, 8, 3, 6, 4, 7, and 5, 9. And you wish to fit a parabola y equals ax squared plus bx plus c to this data. Find the matrix A and the vector y so that you can set up the normal equation. Work out A transpose A transpose y, and write down the vector v in terms of A, B, and C. Solve the matrix equation. Okay, so running it back, essentially. Alright, our A is going to be this. So I'm going to do this. A, I guess VO. I don't really want to do that. I'm going to do A, B, C, just so that we define that, equals Y. And A is going to be our equation. I'm just going to speedrun it. Okay, so our first column is going to be the x squared. So it's going to be 4, 9, 16, 25. Interesting. Our second column is going to be the x, so 2, 3, 4, 5. And then we just have 1, 1, 1, 1. It's a 4 by 3, which is really unfortunate for us. Equals, and then our y's, so 8, 6, 7, 9. Nice. Yeah, we're just gonna do the same thing. We're gonna project. So normal equation. I'm sorry, I'm writing it so far off screen there. Normal equation. All right. A transpose A. Okay. You know, when people ask, like, okay, so you're an engineer, what do you do? I'm like, or you know, people say like, oh, engineering is so hard. And I'm like, okay, it is, but also there's just stuff like this, where it's like, just write down a bunch of numbers. It's like, chat, it's not that bad, okay? Like, really, we're just gonna... I mean, this sucks. It's gonna suck. It's gonna be a 3 by 3. I mean... What are the chances he gives us a parabola? He'd probably just ask us to set up this matrix, not actually do it. If he asked us for us, because there's just so many calculations. Okay, so it's gonna go like... First, inner 1, inner 2. I don't know how to describe it. It's gonna go like 1, 2, 3, 4, 5, 6, you know. They're gonna start to match, but oh, there's no negatives. Okay, we gotta get a calculator. I need to charge my calculator before finals. Actually, fluids might... Well, linear won't make me use it, and fluids maybe won't make me use it either. I didn't use a calculator at all in the last exam. Dude, it's gonna be so annoying to have to do the fluids 3-hour exam. Bro is gonna destroy us. Okay, 9 times 9, 81. I don't know what 16 squared is, and I don't want to say what 25 squared is either. Okay, 987. Sorry, 978. Dyslexia. Okay, so 4 times 2, 8. Plus 9 times 3, 27. Plus 16 times 4. Plus 25 times 5, 125. 224. And then 4 plus 9 plus 16 plus 25. 54. Okay. So then this is going to be 224. And then we have this like second one squared, so that's gonna be the same thing as the last thing. That's gonna be 54, because they're all like squared, and you know, it's squared, whatever. And then we get 2 plus 3 plus 4 plus 5, which is 14. And then let's see, that's the 54. And then 2 plus 3 plus 4 plus, that's 14. And then 4th? Okay, that wasn't actually that bad. I mean, multiplying anything else by this is, you know, not... Oh, no. We have to do the matrix of cofactors. Oh, no. Oh, fuck me, dude. We have to do the inverse of that? Oh, we are so not doing that right now. And by not right now, I mean like we're gonna do y first and then we'll figure it out. Oh no. Oh god. Dude, I served my time in the linear algebra mines in high school. I don't need to be doing inverses of 3x3s, please. Certainly not with 987 as the number, bro. Please. Save me. Okay. Alright. Okay, this one I'm gonna have to also put into calculators. This one's the big numbers. Okay. So 4 times 8 is a number. 8 and 8 is 32. Plus 9 times 6, 54. Plus 16 times 7, I don't know what that is. Plus 25 times 9. 423. And then 16 plus 18 plus 4 times 7 is 28. Plus 45. If I get even one of these numbers wrong, then it's gonna all be wrong, is the thing. 8 and 6, 14, plus 7, 21, plus 9, 30? Okay. Right. A transpose A. Inverse. Let's quick inverse of a 3x3. How to quickly invert a 3x3 matrix. It's the adjoint, but I don't remember how to find the adjoint. Whoa, what? What the what? Whoa, B cross, what? You could do like a cross product thing? Wait, that's kind of cool. If you spend some time thinking about this method carefully, you'll see that you're actually following the steps of the traditional method, but in a quicker, more sophisticated way that actually has meaning. Whoa. That's interesting. Should we try this? Wait. Should we try it? Should we try it, chat? Wait a second, wait a second, wait a second. Take a look at this. Okay. Okay, so let's read this. Let's read this. From 2021. Well, it'll be easy to tell if this is a false thing. So take two vectors. The formula of the cross product is these. The result is a cross product that is perpendicular, sure. Our aim is to find all the elements in the last matrix. Okay. So A by A inverse gives the identity matrix, which is ABC times DEF. Which means that AD, sure. Looking at this column, we can see that BD equals DC equals 0. D is perpendicular to both C and D. Let's see, BD equals CD, or BD equals CD equals 0, sure. D is perpendicular to both B and C, so D is parallel to B cross C. So D equals plus or minus B cross C over B cross C. D, sure, okay, okay, we'll give that, so that, like, is 1. On the first element of the first column, we see that AD equals 1, so AD cosine theta equals 1. Oh, are those dot products? Oh, I think those are dot products. Sure, okay, sure, yeah, they're dot products, yeah. Where, okay, so we put AD cos theta equals 1. Okay, why is it 1 over A cos theta? Probably because if we solve it. Oh, yeah, equals, yeah, okay. where theta is the angle between A and D, because D is parallel to B cross C. Theta is also the angle between A and B cross C. So B cross C, A cosine theta equals B cross C dot A. That's the triple scalar. And what we find, we have one of the column vectors that we were looking for, as long as we know what A, B, and C are, which we do. They are the row vectors of the matrix we are trying to find the inverse of. Giving us the same following argument. For A cross C, A dot B cross C. Because A dot B cross C equals C dot A. Sure, you can use any row to use as the dotted vector. Also, because determinant A equals determinant transpose of A, you can find the determinant by using the columns rather than rows. This means you can find determinant. Okay, sure. Yeah, that was... Oh, hey guys. Here. Hi, how's it going? Kind of feel like managing factory logistics, but I'm too tired to actually do it. Wait, that sounds cool. How's it going? It's going well. I'm looking at this... I have to do... So, we're doing projection. So, best fit equations with the normal equation. And the normal equation requires that you have an inverse. And this is totally fine if you're doing a line, because the inverse is just a 2x2, right? And a 2x2 inverse is fairly easy to find. You just need the determinant, and you need the, you just flip the little things around. But a 3x3, which is what you need if you're doing a parabola, is kind of annoying. So I was looking up, so like the way that I learned to do a quick 3x3, even though I never did it really quickly, was you do like the 1 over the determinant times the adjoint, right? But there's this other way that like I stumbled across on here, and I'm wondering if this is gonna work. So we're doing some little proof analysis thing. It's just Shapes.io. I really want to play it, but it wasn't on Steam somehow. Like I couldn't find the demo for it. I want to try it though. Okay, so we just found that we can use basically like a triple scalar product to solve this. There, demo. I'll have to show. Okay, after we do these problems, then I'll check it out. Okay, and then we have one fluids problem to do, and then I don't really have anything planned, but I was thinking of maybe making up some fluids problems because I'm going to be doing a more formal lecture series on fluids, and I want to have some of my own problems so that people can have like design problems for them. Okay, so A inverse times A, or A times A inverse equals 1, and A times A inverse transpose, identity matrix transpose, A inverse transpose, A transpose. Sure, so B equals A inverse transpose, then B transpose equals whatever. That's just proving that you can use it for the... Dark mode is paid. Oh, it's fine, I like light mode. I'm a masochist. Comparing 5 and 6, yeah, sure. Okay, so we do determinant equals 1.2 cross that, which is easy to do. We can find that. So we just triple scalar either the rows or the columns, I guess, whichever one is easier. And then we do 1, 2, 1 cross 1, so we do B cross C, we do C cross A, and then A cross C. B cross C, C cross A cross B. But in this one they do 1, parallel piping. Okay, they do B cross C, and then they do C cross A. Oh yeah, and then they do A cross B. Okay, so they actually do that. All right, let's try it. Wait, but doing a cross product kind of sucks also. Is that faster? Wait, let me see if there's a quick cross product method, because like the way I know it is like maybe not super quick. Oh my god, that hand is so rough. Jesus Christ. Wait, why is the fingers on the bottom of the... That's scary. The fingernails are on the bottom of the hand. Okay, I think there's no quick way to do it. So let's try it. I would rather do only 3 cross products instead of doing a bunch of adjoint matrices. Although, maybe not. I don't know which one would be faster because... Okay, just for context, this is the matrix we're trying to find the inverse of. It's pretty scuffed. Okay, so if we want to do, like, the dot... I'm already, like, psyching myself out of doing it. I think we should do the adjoint. It'll probably be faster. But I still have to do the determinant of a 3x3, which is like... Well, the determinant we could do the triple product. Triple scalar product. I think. Oh, it just is so bad, though. Yeah, I'd rather do adjoint. Let's say 1 over determinant, because I don't want to do that right now. Okay, so yeah, 54 times 4 minus 14 times 14. Have I seen 9 souls? I have not seen that. What is that? 54 times 4 minus 14 times 14. 188. Yeah, it's not, like, great, but it's not bad either. Okay, so then for 24, it's going to be minus. And we'll get 224 times 4 minus 54 times 14. 140. And then we get a plus, we get 224 times 14. Yeah, this is faster, I think. 220. And then we do minus, what do we get? 224 times 4 minus 54. Oh, it's gonna be... I'll have to put the transpose on. Ooh, cool indie game. I will check it out in a second. Times 14. 140. Oh, it is symmetric, so I guess I could just... I'll just prove to myself that it's symmetric first. 9 times 4 minus 4 times 4. 996 positive, and then times 14 minus... Why does it have to be so big? Why do the numbers have to be so huge? What is 156996? Not me derailing streams so hard right now. Oh, it's okay. I derail streams all the time. I'm the streamer. 220. Okay, that is a positive, yeah. And then a negative. And we're gonna do 7 times 14 minus... Okay, yeah, it is. What the what? Oh. I forgot to hit the times. That should be negative, though, I think. That means that should be negative. Positive, negative. Yeah, oh yeah. Is this vector math? Yeah, it's vector math. It's actually, well, it's matrix math, so it's not... Not exactly vector math. But I mean, vector math is matrix math. This transpose. Wait, that should be this... No. Oh no, it's fine, our transpose will be... Matrix is just wide vector. You're so not wrong. It's correct. It's just like 3 vectors stapled together, is one way you can think about it. I really don't want to do the determinant of that thing. I also don't really want to multiply it by y. Is there any reason I would do this? Like, okay, what I'm trying to think is there any reason why I shouldn't just put these into my calculator and then multiply them? The answer is no, because there's no way he would give us this nasty of a thing. But the thing is, it's because he gave us, like, he would have to give us all, like, 1s and 0s, I think. If he gave us a parabola with 3, he could just give us a regular. Well, no, it has to be a parabola with 4. It'd be over-constrained. Oh, no, is that true? No, you can make a parabola out of any 3 points, right? Yeah. Oh, that's a great question. I don't know. That sucks. I'm gonna do that later. But that's basically it. And then you just have to multiply them. This one... I did. Wait. Did I actually do this one? Are you meta-analyzing the problem for the solution? Oh, kind of. So, like... what I think is a good thing to do when you're studying for a course, if you have the capacity to do so, is to understand the line between what you need to know and what your professor is going to ask you for. So, like, for example, the reason why... So, if you're doing this... And also, like, the third thing is, like, in the real world, what you would use it for. So, like, take this problem, for example. If I needed to solve this problem in the real world, this is asking for a best fit parabola, and I have some data. The likelihood of me doing this by hand is very slim. This is a thing that Excel can do. It's an important thing to know how to do, how it works, what you're doing. But if I have actual dimensionful data, and not like, for example, functions, you wouldn't be doing it by hand. Now, if you were doing it with functions, you'd probably be doing it with MATLAB or something, and you'd have to write some code for that. I mean, you can also write code for this. But that's sort of the point, is that I'm thinking about this, I'm saying, like, okay, is this going to be asked of me on a test, right? That's the reason why you would be doing it by hand. And the answer is no, because he doesn't give us a calculator, and there's no way he's going to give us 22636 as a number oh, it's 2636, not 22636. Your school would give you that? Well, but that, yeah, it depends on the professor, right? Like, for example, my fluids professor would give us an entire long-ass problem to do and then make us do it all out with the units, otherwise he gives us 0 points. Right, so, like, knowing that and knowing, like, what time you need to spend on certain things is useful. Obviously, I think it's interesting because I've almost never thought about that, because I don't think it's good to think about tests in a way where it's like, let me do the stuff that's the most points first, because it's like, you should really be doing everything. Like, if it's a test that's good, you should be able to complete the whole test, so there's no point to saying, like, let me try to do the things that are worth the most points first, because you should just do it and know how to, like, skip around and, like, come back to things. I'm just trying to think. This, piecewise, I mean, I could split it up into 2... Not really. I couldn't really split it up into 2 intervals. I think this is right, though. It seems sort of right. It's orthogonalized. I just didn't do this out yet. I guess we could do that. Oh. Wait. That was my first attempt at 6. This is my actual 6 old. But yeah, I mean, it's more like, what the, oh, I forgot I didn't orthogonalize these. I found a math streamer. I have a small question. Do you know any relationship between the minimal polynomial of a matrix and its possible Jordan normal canonical forms? Welcome, Ohio world. Oh, Ohio. The minimal polynomial of a matrix and its possible Jordan normal canonical forms, except that the minimal polynomial divides the characteristic polynomial. So, a little bit of context. I'm an engineer. I'm not a math major. I can't answer that question greatly. There is something in my mind where I snuck into another professor who didn't teach my linear analysis class, I snuck into a different professor than mine's class because he taught the class better than my professor did. And he did talk about that because he talked about Jordan normal forms and my actual professor didn't. So there's I mean, you can talk about, like, I don't know what you mean minimal polynomial of a matrix. I think I vaguely remember that, but I will say when we talked about Jordan normal form, it was about like eigenvalues and how many eigenvalues you had. Although I will also say, like, we only talked about one Jordan normal form, and this was like for 2x2 matrices only. So, because we were talking about them with respect to, like, phase spaces, and whether you could find, like, essentially, like, a matrix that was, like, close to that matrix, right? Like, that's sort of what we were doing it for. So, unfortunately, I cannot answer your question, but maybe some of the things that I said might lead you in the right way if you're going to be doing Google searches. Trying to think if there's anyone I know who's, like, more into matrix stuff. A lot of the people I know, like, a topological guy. I know, like, more of a proofs guy. I don't really know anybody who's super specifically into matrix or tensor or vector stuff, unfortunately, off the top of my head. I can't believe I did all this out. I don't need to do all this out. I'm just gonna redo this, I think. As an engineer, I would have assumed that these matrix manipulations are used in application often because they are really OP. Oh yeah. Oh yeah, that's why we sort of talked about it. Oh my gosh, next month is my favorite surprise once they came out. That's so exciting. Oh, that's like the best time. Oh, an engineer. They are sort of, how do I put this? It's like the things that we use. Or okay, actually, let me give, like, a better explanation. I'm almost done with my second year of engineering, and I'm finally getting to the point where, like, most people now have done prerequisites for courses where those courses now actually involve doing real math, because a lot of the math that you tend to do as an engineer, ironically, is mostly algebra, and you don't really need a lot of calculus for things until you start doing more complex geometries. But you can kind of get away, a lot of the classes just kind of get away with simplifying everything into not doing calculus or not doing linear specifically. So, like, yes, I mean, I can think of, like, one of the things that we might want to use, like, diagonalization for, or, like, eigenvalues for, is, like, for example, in stress analysis, if you have, like, a stress test. Chicken on screen. 2 types of damie viewer. 1, math jargon, I have no clue. 2, OG chicken. I love both of you, though. That's great. I love chickens. But yeah, stress state analysis, we do need to find, like, for example, if we want to find, if we do a bunch of tensile tests, we find a bunch of numbers about these stress states, and we go, oh, we want to find the elastic modulus and Poisson's ratio. You need to find eigenvalues to do that. But it's relatively simple. It's just, like, you know, that kind of stuff. I think we tend to use differential a lot more than we tend to use matrices, which it actually is, like, fascinating to me and, like, depressing. Like, I'm almost in my 3rd year. I'm taking, like, fluid mechanics, and I'm gonna be taking, like, heat transfer soon, like thermo, heat transfer, that kind of stuff. People still write vectors as, like, and professors do that. So it's pretty bad. Like, people are pretty allergic to math. And to be fair, like, the kind of analysis I'm doing is not, like, it's not really, like, it's so weird. It's, like, not high-level engineering, but it's not only design engineering. Wait till you differentiate matrices, you probably already did that. I mean, we've done that with functions, but, like, a lot of it is just, like, you don't use it until, like, your senior year, which is so stupid. I mean, like, And they don't, like, it's fucking dumb. I mean, like, this is why, like, I try and teach people. That's why I stream, because I'm like, I want to teach people, like, the math they actually need, and also teach them math that's, like, fun. You know what I mean? Like, there should be math that you learn because you want to learn math, and there should be math that you need to learn because you need to use it. And, like, for example, they don't teach people cross products until, like, fucking, like, linear, or, like, because they don't actually know what a matrix is, right? Until, like, they actually start taking linear algebra. And then by that point, it's like, dude, you've taken fucking, like, 3 classes that require you to, like, just do cross products without knowing what they are, actually. It's like, guys, fucking don't do that. It's like, oh, you're an engineer. You need to do Navier-Stokes. You need to do, you know, these heat transfer equations. We're not going to tell you what a partial differential is. You're never going to take a class on partial differential equations. Figure it out. It's so nonsensical, because people don't want to take... A lot of people don't like math. Like, and they are somehow in engineering. I don't know. It's scuffed. But, I do want to... I want to learn more linear stuff if I can. Or more, like, applied... I try to apply linear as much as I can, because, God, it makes your life so much easier. I'm gonna have to, I wonder if I could just state that this is not the orthogonal basis. Can I orthogonalize it? What do you think, chat? Do we orthogonalize it? Or should I just say what it is? Ironically, though, I think this wouldn't be right. I think it's this. I think that's what they're saying. But I don't know if that would really give me any different results if I orthogonalize it. It probably would. Because this is not orthogonal to this. Or 1 and x. Well, I guess it depends on the... It's also over, what? 1, 0? Negative 1, 1? Oh, beautiful world. I do love a good negative 1, 1 symmetric basis. Symmetric interval. The duality of damie. I don't know. I want it to be x squared so I don't have to actually do this out. Although it's not really that bad because the integral's for it. Did we give the Mike Demon a name? I think I called him Ro. Because, like, the Pharaoh's curse. And so I shortened Pharaoh to Ro. But I don't know. I can't remember. I think his name would be Unspeakable. I did draw him. He kind of looks like this. His name would be the sound he makes. Yeah, that's what I was thinking too. One of the sounds he makes. I don't want him to say his name this stream. That would be great if he didn't. Yeah, I think I gave him like little... One of... I don't know if it's consistent, because sometimes when it used to happen, like, it would modulate with my voice, actually. But I don't know if it's just... It looks like it's just this. Like, it's so funny because I have to edit it out of all my VODs. The exercise is just keep kicking the microphone until it stops. My VODs will look like this. This is... Like, this is what this waveform looks like. It's just like, oh, talking normally. Oh, you know, like, oh, talking normally. And then just a wave. It's like literally so much noise and so dense that it just becomes a white bar. It's just crazy. I'm gonna have to ask him about this. I'm gonna leave it as x squared. And we're gonna state the orthogonal basis. GSOP proved in class. He's gonna hate that. It's 1x 1/3 x 1/2 x squared plus 3. 3x squared plus, no, 1/3 3x squared plus 1. I mean, the most important part is the projection of sine x, right? So, alright, here we go. This is gonna be sine x 1 1 1 1 plus sine x x. Oh god, I love integrals that are gonna be even and odd. Dude, that was such, like, when he started talking about even and odd functions, the fact that, like, if you have an odd function over an interval that's symmetric, that its integral is just 0, that's like the most cracked thing ever. I can't believe they don't, like, emphasize that more. He was like, yeah, because he, like, teaches lots of calc and all that stuff. He was like, yeah, when I teach calc 2, I'm gonna start saying this more. I'm like, dude, you would have saved me so much time in so many places, because if you don't have a symmetric interval, it's just so annoying to do. Like, truly. Okay, we got lots of inner products here. There we go. Squared. Squared. I think that's everything. Okay, and yeah, I'm using the orthogonal basis, so we're all good there. Alright. Do that. Alright, sine is an odd function. Entire thing goes to 0. Don't even have to worry about it. Sine x is... oh, stretch? I'm gonna get up and stretch my legs. You know, I sit, like... there's one thing that I want to do still, and there's one thing I was thinking about doing. Was, so I sit kind of... and I was gonna have my... okay, well now I have to stretch a lot, thanks. What else is there to stretch? My back, I guess. Oh my god, why are you making stretch him Saturday, stretch him Sunday? Oh my god, I'm so stretched. You're pulling me out. What the well, this is gonna go on for a while. How many of those do you you just keep going? Oh my god, how many is that? That's the most anyone's ever stretch. One word. Bro, you're trying to determine my elastic modulus right now. Doing 23 tensile tests to find my 26 linearly independent elastic moduli in all of the directions. Hey, that is a fun matrix application. You like 6x6 matrices? Just D1 to D6 to D1 6. That's a stress matrix, baby. Stretch. It's a big ass matrix. No zeros if you don't play your cards right. Okay, so sine x times x is, well, I guess I should probably write the integral. X over x times x, that's gonna be an even, so that'll be chill. I really should save points up? For what? I already am gonna do the textbook reading. I love that. When did I promise that? Like, that was like, no, that was over winter, I think. Maybe not, I don't know. It's at like 2K, oh my god. I gotta have a bet at some point so you guys can waste all your... I'm kidding, I would feel bad if you wasted all your points. The textbook reading, I need to think about what textbook I want to do. I don't know what textbook I should do. I did not for gore. It's gonna be this summer. I just wanted to be able to do it, like, once my voice dropped, and I also had my new model. I think those were my two. Those are generally my two reasons for doing anything, for not doing something. Like the Beat Saber physics stream. Mostly because I'm like, I want my voice to drop. And, wait, these all cancel out. Yeah. Generally my reasons. Or I wanted, before I went on T, I wanted my voice drop. What is that? Sine x 3x squared plus sine x. Oh, that's gonna be 0. That's gonna be 0. Odd. This is odd times even. Odd. Yes! 0! Whole term is just 0. Oh my god, it's so clean. Oh my god, another stretch. Okay. I've been stretching a lot lately. Well, actually, it's true. I've been doing a lot of lion dance stuff, so we have to stretch a lot. Let's see, this is an odd times an odd. Good, we have one even term. Oh, I do have to do integration by parts once. Okay, so this is gonna be 2 times 1/3. It's like 1 oh, it's a 3/2 times 2. Okay. And then we just have 0 to 1 x sine x. That is so beautiful. And then this times x, obviously. Alright, so x sine x, not a recursive integral. It's like f, what am I doing usually? F prime, x, 1, 0, g, Sine x, negative cos x, negative sine x, plus minus. So chill. Okay, so 3. This is so chill. It's literally just 3, and then negative x cosine x plus sine x from 0 to 1. Oh my god. Or this also times x. Oh, wait, it should be a line, yeah. That makes sense. Over such a small interval. Okay, so for 1, we're gonna get, what's cosine of 1? Wait, cosine of 1? Good thing I didn't say anything there. The cosine of 1 is like nothing. Well, it's not nothing, but it's just not something that we know. So negative cosine of 1 plus sine of 1 x. Oh, and we do have to do the we have to do the 0 because they're not always going to be 0. Lol. Okay, well, so 3, let's see, negative cosine of 1 plus sine of 1 minus, oh, I should put on Super Paper Mario. Okay, cosine of 0 is 1, so, but it's 0 because of the x, and then sine of 1, sine of 0 is 0, it's 0, okay, never mind. Okay, what is this number? Should we try and graph it? Let's see. If it looks really messed up, I'm gonna be really depressed. Okay, hide that. Okay, so first we need to plot sine of x. Looks like that. Our favorite buddy, sine of x. Then we need to plot 3 negative cosine of 1 plus sine of 1 x. That's pretty good. That's pretty good. Look at that. Over this interval from Wait, if I edit this... -1. Oops. The 1. That's pretty good. That's pretty good, right, Chad? Look at that. I mean, that's assuming that we're actually doing it on the basis that we did it on. That's pretty good, though. I assume that he meant that, but you know. If not, then, you know, we'll fix it later. Okay, so the old ones I can move somewhere else. Let's see, 5 we did. 1. What the hell was I doing here? Oh, explaining something. 2. Oh yeah, 2 was weird. I'll have to look at 2 later. Oh yeah, after let me just check that we did 3. Yeah, we did 3. Okay, cool. Yeah, I think we are good. That one I have to do the transpose of. That one's fine. That one's fine. That one's fine. That one's fine. Okay, perfect. Okay, we are gonna do a fluids problem, but let me see these links. Okay, what links did we send? We said the shapes. Oh, sorry, I'm checking. I don't know when you're finished doing anything. Yeah, no, it's okay. It was actually good timing. Okay, 9 souls. And then... shapes demo. Okay. Whoa. Wait, this is just like a thing? Wait, I could just like play this right now? That's hype. Okay, I like that. And then let me see. Let's grab 9 souls. Wait, I gotta pause it. Wait. Okay. 9 souls. A lore-rich, hand-drawn... Ooh, I like the protagonist. Featuring Sekiro-inspired deflection-focused combat. Ooh. Very small. And now it's very big. It looks interesting. I'm back. Row gaming, yeah. Wait, whoa, Chinese mentioned. What did that say? What did that say? Wait, no, go back. Woman, sure. Thai something that I can't read. We are very... What is that character? Wait, I need to know what that character is. It's traditional, so there's a chance I know what that character is. Wait, I'm sorry, I'm pulling up my... I love Chinese, guys. It's such an awesome language. That is a hard to write character. No, it's not, I lied. What is it? Yang? What? Wait, maybe Thai is part of that. Maybe it's a word, Tai Yang. We are... Oh, we're the sun. Tai Yang. Or Tai Yang. We are very sun. Tai Yang Chuang. Sun window. Roof of car. Huh. I've never heard of it referred to it that way because I always think of Sun as like the very simple character. But I guess Taeyang could be sunlight, but maybe that's like the soul. Taeyang. Sun's rays, yeah. Well, there we go. Sorry. Got distracted. Oh, Joe. Oh, it's a pun. It's a pun. It's called Nine Suns, but like soul, like solar soul. Ah, I get it. That makes sense. That makes sense. Okay, sorry. That was like. It looks cool. It does. I will say it has that like sort of vibe where like I can tell that like the character is not entirely integrated into the background, but I think it's because of the line weight differences or something. I don't know. It looks cool though. Oh, okay, I want to see what this is. I don't know if this is making noise. I'm gonna mute it. I can't mute it. It's not making any noise. Whoa. Okay. This is... Oh my god. Cherry Blossom Tree from Katamari. I'm dying. Place an extractor on top of a circle shape to extract it. Connect the extractor with a conveyor belt to your hub. Okay, well that's not the most efficient way of doing that. I'm kidding. This is not an idle game. Build more extractors and belts to finish the goal quicker. Hold shift to place multiple extractors and R to rotate them. Wait, does this one go on too? Can I do this? You can't do multiple ones? How do I get rid of it? Delete. Oh, there we go. God damn. Oh. Hold shift when placing conveyors, by the way. Oh, can unlock cutter, which cuts shapes in half from top to from top to bottom, regardless of orientation. I want to get rid of everything. Get out of here. Get out of here. I don't know. Wait, I don't want that either. I lied. Get out of here. I see, so there'll be one which is good, and then one which is bad. How did this get rotated? Hey, dude. Sorry, I'm too used to like oxygen not included systems now, and I'm like, I'm spoiled, you know? Everything's like awesome there. And I don't have to like, you know, worry about anything. Okay, so can I or can I not put them? I can't put them together if I put shift? No, I can't. I have... God damn it. Oh, it'll get clogged if trash. I can't put stuff over other stuff either. Wait, I can just put a trash can. Lol. You unlock... What is this? This is something called shapes.io. Place 2 more cutters to speed up this thing faster. Well, I mean I could, or I could just wait, because I'm a patient boy. I'm a patient man. Okay, see? That's fine. All shapes you produce can be used to unlock upgrades. Don't destroy your old factories. They can be shown. But, like, I feel like it's weird because it doesn't, like... Oh, okay. Sure. It doesn't, like... Oh. It doesn't, like, it doesn't take any resources to, like, do stuff. Like, I can just build infinite things, which I feel like is kind of, like, weird. Do you know what I mean? I feel like you should be... I feel like you should be limited. It's pure factory. It's off-center. The feed. Oh, it's cropped. Yeah, it's not... I can uncrop it a little bit. I do know that it's cropped. I just... I don't usually uncrop it. Where is it? Browser. Because I don't want to. It's like I either can crop at the top or like I can leave it. It's like what actually? Wait. Sorry. Okay, there we go. Oh, I forgot I can actually wait. I can actually go all the way up. Not exactly. Almost all the way up. There we go. Wait, fit to screen. I don't know where this button is. It did some. Oh god, everything's happening quickly. I like how it says it's not an idle game. Engineering is sort of an idle game. I don't know what it just said. I didn't pay attention. Can I click save? Oh. Okay, we'll get out of here. Unlock rotating? Oh, you're trying to say how long I follow myself? Wait, how do I upgrade this stuff? Oh, I just have to put this. Wait, I can still put the stuff in there? It'll take it? Wait, but I don't want cutting. Wait, I'm confused. Does it want me to put these things in here or not? Okay, this is scuffed as hell. Oh my god. Oh, I don't know if I like this. Go the way that I want through it. Does it give me stuff? Oh, it does. Interesting. So I can upgrade that. Oh, I see. Wait, but how do I put multiple? I feel like you have to be able to put multiple things into the thing, right? That's what I'm getting confused about here. It's not going in. There we go. This is very interesting. What did it want me to do? Oh, this thing. Oh, half of those. Okay. Oh, I don't want that there, though. Oops. I'm literally so used to the Oxford not included in controls. I don't want. What if I want like? Oh wait. Wait. This. And then get rid of those. I guess. I don't know. This is weird. Okay, I swear I'm gonna do fluids in a second, and then we can play this if I do a good job at fluids and I'm awesome and I win. Does that work? Does it actually let me do that? Oh, it does. Okay. Okay, that's sick. Look at this, guys. So good at this game. Wait, why is it? Wait, am I delivering the wrong half of them? How do I deliver the other half of them? Oh, this one. Whoops. I'm just throwing out all of the halves. It's really funny. Wait, can I just put it right there? Mega efficiency. Nobody understands. Nobody understands. Look at this. Watch this. Oh, wait, that blocks it. That's actually dumb. That's not mega efficient. That's just dumb. Can I wait? Okay, can I flip this so that it like goes the other way? I like rotate it left to right. You know what I mean? I mean, I guess I could do this. Maybe that. I want this one, I think. Oh yeah, baby. that right? Maybe? That's cool. The rotator has been up. Okay, it rotates them. Okay. I don't really care about keyboards. I'm too cool for keyboard. I'm kidding. Fuck, I keep... Oxygen not included drag is not like drag. It's right click to drag. So what is this? What is this? I don't need this there. I can just do that. It is weird to me that like you don't need resources to do stuff. Like I feel like it should cost like stuff to do the stuff, you know? Also, this is inefficient. Get out of here. It's red? What's red? I don't know what's red. Oh, it's not going the right way. God damn it. Get out of here. Wait, so you just need to like... To be the most efficient, you just need to like... I really wish you could combine conveyor belts. I feel like that would be like the best thing, you know? What is this? I don't know what that is. Oh, that's the rotator that we just got? No. I don't know. What if I just put both of them in? Did the other ones do anything? Oh, I need the bottoms. Oh, it doesn't like me giving them the sides. Okay, wait, I have to rotate them. Can I just put a rotator? Is this the rotator? No, balancer. What? That's a rotator. Oh, I see, it just literally rotates them like that. Gameplay is realize what shape you have to make, spend 2 weeks designing an ultra complicated factory, then complete that shape, then deleting all your hard work. I mean, that's like kind of frustrating, you know? Oh, I just have to, wait, can I rotate them the other way? Hey guys, let me show you like a cool hack. 3 lefts make a right. Don't worry about it. This is cool, I could get into this. Okay, we need to do a fluids problem before I do this more. How do I pause it? Can I pause it? Can I quit it? Is it gonna let me quit it? Wait, stored? Oh. Oh, so like even if I don't produce it, like it's okay. Is it gonna let me exit? Oh, okay. Okay, we're gonna do no pausing. It's fine. I deleted it. Okay, yes, pausing. Oh, my music stopped. Wait a second, let's bring that back. I don't know, let's do Mario Sunshine. I gotta go. Oh, okay. No worries. I'm gonna do fluids. We're doing a fluids problem. Oh my god, this... What the what? That's a crazy factory. Which auto emote can go? Wait, no, it's cute though. Wait, what did I need to do? Fluids. Oh, it's a thermal problem. It's okay. We're gonna... It's okay. I'm saying this for myself. I'm not saying this for you guys. I'm trying to, like, calm myself like a scared horse. I was thinking about fluid stuff, because I wanna come up with some problems for... I think I've come up with some good questions. But I'm not sure. But like, ah is way better than ah. No, it's cute. Well, okay, it evokes a different emotion. But you have to be ready, you know, you have to be ready for that. Okay, here we go. Oh my god, he's such a... My professor talks like an NPC who's annoyed at you in a video game. That is the best way that I can describe it. Like, evil. He'll be like, Only you could look this up in some sort of game guide. Like, so funny. Oblivion? Yeah. Oh my gosh, the little tongue emote, the bleh. See ya. Have a good day. I think I want to play more. That Shapes game is like, okay, that's kind of like brain good. And don't forget, stretch. Okay, I'm stretching right now. Oh god, there's so much. Okay. Air flows through a long duct of constant cross-sectional area so we have a flow. We're also in metric units. Bye, have a good day. A short section of the duct is cooled by flowing liquid nitrogen that surrounds the duct. Okay. Thinking about oxygen not included. It's okay. I got it. I know what these things are. It's so funny to me. One guy who doesn't know how to do engineering at all was like, I played engineering video games. I should know how to do this. The rate of heat transfer in this section. Okay, so it gives us the rate of heat transfer. That's a d by dt. So we do not have steady flow. We have not steady state. Okay. The absolute pressure, temperature, and velocity entering the short section of the duct are those things. At the outlet of the short section, we're given the absolute pressure and temperature. Okay, so we have information. Talk about an ideal gas. We can talk about density. We don't have constant density, obviously, so it's not incompressible, but we can find the density. We're given temperature. Usually if we're given temperature, we can find a density. If we don't have it, then it's like, we probably have to assume it's incompressible. Calculate the velocity at the outlet of the short section. Okay, velocity at the outlet of the short section. Probably a mass flow question. The cross-sectional area of the duct. What? Wait a second. Okay, wait. I thought it said constant cross-sectional area, and I just looked at the number, and it said the cross-sectional area. It's not the cross-sectional area. That's like kg per second. It's flow. It's not. Oh, that's funny. Okay, that's a mass flow. That's a mass flow rate. Oh, so we're given an m dot. Interesting. We'll figure that out. The change in internal energy between the inlet and outlet of the short section. You're not given a schematic, so you must draw one in order to show your selection and control volume. It would also be helpful for you to visualize the situation described. Alright. Okay. Math with Nintendo music in the background is just perfect? Absolutely, I agree. I think either Nintendo music or the Doom OST are my favorites. You gotta really get into it, you know? This is a property that you can look up. If only there was a handbook with supplemental information like this, right? So... Okay, we need a schematic. Let's start with a schematic. Let's draw a duct. We know about ducts. Well, they're square. It's cool. Alright, so it's a long duct, so I don't know. It's long, it's square. A short section of the duct is cooled by flowing liquid nitrogen, so there's like a... This is gonna be the liquid nitrogen portion. What is that? N2? I don't know. The only thing they fear is you. Yes! So good. Delfino Square? Yeah, I love Sunshine music. It's such a good summer. Such a good, like, oh my god, I'm almost done with exams. It's hot out and I don't want to be doing this. But I have to be doing it. Alright, sick. Okay. Cool. I think that's really all we need for a schematic. Did I spell schematic right? Yes. Alright, control volume. I don't know, what are we feeling? Well, I'm gonna guess we gotta do this. Probably this. We know in and out, and it is a duct, so I'm gonna say... We know... pressures. Do we know the pressure of... the internal pressure? We know the entrance and we know the exit, I guess. We don't know anything about the pressure. Oh, it doesn't really matter, actually, because we're not examining mass flow across that, so we'll call it in here. If we were cutting it in half and we wanted to find some like lift or, you know, drag or sort of other behavior, we're gonna do that though. We'll draw our CV now. All right, I'm gonna do left is in and the DA1. I guess it's a short section, but you know, it's not the shortest section that I drew here, but here's our DA1. We do need to think about coordinate system. It's Cartesian. I don't think it really matters. I mean, we could do it from the middle. Does that really matter? Are we doing R cross Fs? No. I'm gonna go with this. We're gonna go with a cute little Cartesian coordinate system. That. And then we need another area vector at the end. Nice little pipe flow. Sort of pipe flow. I mean, it's incompressible. I mean, it's compressible pipe flow, which we don't particularly like doing that by hand. It's not really how we do that. Stretch? Oh my gosh, thank you. I've gotten a lot of stretches today. Really so stretched out. I should have a posture check too, bro. My posture is getting worse. I feel like it's one of those things where like I'm at a point where I'm like, I should have better posture, but then I think about it, but I don't do anything about it, and I'm like, God, falling back into my old ways. Alright, so we got velocities, we got that. Gotta do some Q dots. Okay. We're given a rate of heat transfer. Oh, I guess we should make some assumptions. That would probably be also good. Well, there's gonna be a lot of things that we normally assume that we're not gonna be able to assume, so that's kind of fun. I don't really know what we should do for one. It's not steady. There's a rate of heat transfer. So, rate of heat transfer from the air to the liquid nitrogen. Okay, from the air inside to the liquid nitrogen, so it's going out. We'll do Q dot air to N. Call that one. And then let's see, what assumptions shall we make? We can assume, I mean, maybe assuming pressure over, pressure is constant over control surfaces might be a good one. Also, velocity is constant over control surfaces would probably be a good one. I could just say properties constant over. Let's try that. Over CS's. And let's see, so we've got that Q dot. Okay, do we have any work happening? Well, not really. I mean, let's see, what are our four types of work? Well, we have the flow work, which is gonna show up as our pressure over density, which the density will then turn into like, we're gonna cancel some stuff out. We're gonna get some RT stuff. We're gonna get, we don't have any shaft work that's happening, we don't have any electrical work that's happening, and we don't really have any normal forces. Oh, we do have pressures. Gotta draw some forces there. Didn't even draw our forces. What is this world? Okay, pressure's gonna act in. But our pressure forces are our normal forces, which is our flow force, so that's already sort of taken care of. In that term that's going to be on the right-hand side of our Reynolds transport. And then we don't really have, like, shear, though. I mean, I guess I could say neglect shear effects. That would probably be a good one, too. We're not really caring about the velocity profile. Ooh. Well, I'm not assuming inviscid flow. I'm neglecting the shear at walls of vent. Of duct. Whoops. Vent. I gotta sleep. It's 2 AM in France. Very good demonstration, by the way. Oh, thank you. Have a good sleep. I know, my streams are kind of rough for EU people. I feel bad. I'll still be here, it's okay. And then FP2. Getting a little big on this small control volume, but that's fine. Alright, we need the velocity at the outlet. We're given... Air flows through a long duct of constant cross-sectional area at 0.5 kilograms per second. Are we... well... okay. We need to do conservation mass first. Let's not waste any more time. Kidding. It's not a waste of time. It's gonna be chill. Oh, wait. Okay. We need... it's steady flow, but it's not steady state, is what I think we need to say. Because is the rate of air moving across the control surfaces unequal? And I think the answer is no for that. But the rate of Q is not 0. Or there is a Q dot. I'm gonna say steady flow. Most things are steady flow. Anyway, so. Do I want to actually do this out? I guess I should. CV, rho, dv, plus CS1. I'm going to say CS. No, I'll say CS1. Rho 1, V1. Okay, no, this is actually important. It's going to be different densities. And that's why we check our stuff. A2. This is going to be a negative, this is going to be a positive, and then we get rho 1, V1, A1, or rho 1, V1 equals rho 2, V2. Oh, and then we just say this. We say V2 equals rho 1 over rho 1 V1 over rho 2. Are we given a V1? Yep, we're given a V1 meters per second. We just have to deal with these densities. We're gonna assume ideal gas real quick before we run too far into the woods without that, because we are not gonna have a good time if we don't assume an ideal gas. We're gonna say rho equals pressure over RT. Is that right? Maybe? I think so. Check my handout real quick. Rho equals... yeah, P over RT. It's specific bar, but like we don't really care about that right now because we're not going to be doing anything with it. Actually, they're both air. The R's are going to cancel out. Well, some stuff is going to cancel out. So we have V2 equals P1 over T1. P1 T1 V1 over, I guess what, P2 T2 P2 T2 P2 I don't like the way I wrote that. Let me write that a little better. E1 V1 T2. Look at that, so clean, so nice. I love it when things are clean and nice. Okay, so that wasn't actually too painful. I thought it was going to be more painful. That's kind of cool. Alright, so that's A. And then we also have to find the cross-sectional area of the duct. Okay. Really not that bad. If we assume that... the velocity is uniform, which we also did, we can do some little calculations. We can say m dot 1, or I guess like q equals... oh, we can just do this at the beginning. We could easily do this. So q equals m dot over m. No, m dot over density, geez. Is that right? Yeah. So, n equals, the average equals VA, essentially. Like V1A1. We'll do that. Q1. I think it gives us, yeah, I mean, this means we're gonna have a constant mass flow, which makes sense because it's pipe, right? Where would the air be going other than out the other side of the pipe? Unless we were accumulating air somehow, or there was like a, if there was, you know, maybe there was a block in the other end of the pipe and it let air out at a smaller rate or something, then we could have a lesser air there. What do we want to find though? We want to find that A1. So A1 equals, it's really quite simple, m dot 1. And then, I mean, the density, right, is going to be that P1, R1, T1. And R1 is specific, so, you know, it's for air. It's not exactly, this is like 99, no, it's like 2 something? Like, order of 100 or something like that. M1, R1, m dot 1, R1, T1 over P1, V1? Dude. This thermo shit is easy. Okay, I shouldn't say that. I shouldn't say that. It's gonna bite me in the ass when I start doing this internal energy one. Okay, here we go. Change in internal energy between the inlet and outlet. Which, ironically, I feel like is slightly easier than the other problem. So the other problem we did was this one, which kind of looks a lot harder. It's really not that much harder, it's actually kind of easy. Pretty much everything cancels out, but the hard part is you have to recognize what stuff you're given. And so, you also have to choose your control volume very specifically. I chose mine to be this pump. We're trying to find the pressure difference across the pump. But, like, it could be so rough if you try and, like, cut through the pump. Or, like, add the electrical cord of the pump in there. Or, like, you know, stuff like that. So, I don't even know if I actually did that right. But that's fine. You know, we took a crack at it. Alright. So that's good. That was what we did before. I am not going to have enough space to do the, wait, what problem is this? Problem number 2. 2-1. I'm also going to have to look, so we were doing, Navier-Stokes, which is super exciting. Very cool. Partial differential stuff, which isn't that hard. I don't know what to say. It's not that bad. Like, I mean, honestly, even partial differential equations aren't that bad. I mean, I know one way of solving them with, like, the phi method with, like, the little trident guy, and you take partials and you, like, set them equal to each other and stuff like that. That was for only first order, though. But, like, I don't know. I don't think they're that bad. I think it just kind of depends on if you learn them or not, which is generally the stopping block for people. First law of thermo, which says that we have q dot in our case it is q dot out, equals, we don't have any work, well, I mean we do, but it's over here, d by dt over the control volume of E, little e, rho dv, that's going to be 0, we did say it was a steady state, plus control surface 1, E plus P1 over rho 1, rho 1 V1 dot dA1, chunky term, CS2, E plus P2, E2, E1, E2, rho 1, E2, oh my god, my subscripts, V2 dot dA2. Lots of good things in here. Okay, so we are given Q out, So we don't have to worry about that. We're trying to solve for the internal energy difference, which we're going to get when we expand these E terms. This P1 over rho 1, though, I think we should take care of, and I think we should take care of the cross product, stuff like that. So this is going to be a negative, it's going to be positive. We can start pulling stuff out of the integral, too. Yeah, let's start with that. So q dot out equals. So we're going to pull this out. Yeah, rho 1. And then we're gonna say CS1. So our E is gonna be V1 squared over 2 plus GZ. Our potential energy is not changing, so I'm just gonna get rid of that. Plus U1. It's little U1. Now I'm very interested because the change in internal energy here. We're trying to find the change in internal energy. Why would you... Why would you give us this? Like... Do we not have to solve for this using... Ooh, absolute pressure also. Let's check that we don't need to worry about that. If I work in gauge, I'm gonna work in absolute. We'll make a note of that. No. We'll do gauge, actually. We'll just subtract an atmosphere from everything. I don't really want to deal with pressure forces on the outside of stuff. I don't understand why he would give us this. Because can you figure this out? The change in internal energy between the inlet and outlet of the duct. Do we not want to just, like, prove that? Is it not an ideal gas? Can I not assume that? I mean, if it's not an ideal gas, it means I can't do all this stuff. I don't know, let's just go along with this and we'll see. So I pulled that P1 out, I'm gonna pull a V out as well. Because we had assumed that it was constant over the control surfaces. And then we have just dA. This is a negative also. Not forget that, that's pretty important. Basically the same thing here. So we switch everything for 2. So what I was going to do is I was just going to say that the internal energy was constant over it and then solve. Well, oh. I see. Well, no, wait, why, yeah, what, never mind. What am I seeing? I'm not seeing anything. I was gonna say that the internal energy is constant over the control surface, so I could just pull it out as a constant over the integral. Would it be? Okay, maybe that's a good question. It's a function of the temperature, right? So it would be, because we said the temperature is constant across the control surface. Like, is that just to, like, check the answer? I don't know what to say. Okay, we'll just keep plodding along, I guess. Negative Q out equals... Wait, did he give us the... Yeah, he gave us the heat transfer. I don't know, man. That's weird. Okay. So, this will be P1 over R T1. Those are all things we know. Now, if we pull out this right here, we're gonna get V1 squared over 2A plus U1A. Might just be because we can't actually, like, factor everything out. That might be why. And so we have to kind of... I don't understand because he literally gives us the temperatures there. Rugs. I don't know, man. What am I gonna do about it? Some problem. Okay, here we go. B2 squared over 2a plus... I mean, I guess I could just pull the a out, right? Let's do that. Ooh. I was gonna say q, we can't actually pull that out, but whatever. So there's our minus u1 that's stuck in there, and our minus u2, and these v2s are different, and all these values are kind of different. I see why he would be like, you can't pull that out. There's gotta be a way, though. Maybe not. I mean, I guess I could, like, try and complete the square. God forbid. Change in internal energy. What am I trying to find, though? Am I not trying to find... It literally says the change in internal energy between two states is CV, C2 minus T1. The absolute pressure, temperature, and velocity entering the short section of the duct gives a temperature. At the outlet of the short section of the duct gives us a temperature. What the... what? I mean, I got this far. Like, we're just trying to find the... Okay, if I was trying to solve for this, how would I even... Okay, I can do this, Let's just try and get them on the same side. So... negative a p1... Oh, no, negative a over r. So those are the similarities. No, sorry, a over r. Sorry. Negative p1 over t1 v1 u1 plus e2 over t2 v2 u2 equals negative q out plus, oh my god, okay, p1 v1 cubed a over rt2 rt1 plus or minus p2 v2 cubed a over r2 rt squared t2. Well, that's something. I mean, I don't know, that's so weird. Like, if I was trying to solve for Q out, I could solve for Q out, you know? Because I could get the U1s and then figure out the change in internal energy. I mean, if it was an integral, it still wouldn't really change anything. Like, we could still try and solve for it, but it's just that these values are not really, like, we can't really consolidate it, is the thing. That's so weird. Maybe he does just want us to do the temperatures, or maybe he forgot that we shouldn't have the... Okay, wait a second. If I go to the... Because I think he provided an answer for this one, I'm not sure. He did provide an answer. Also, I didn't plug in any numbers, but... So it's negative 190 kilojoules per kilogram. Oh, no, internal energy is still U. Yeah, what? Wait, so T1 minus T2, or T2 minus T1. Let me just do this. 350 minus 3, or sorry, it's 351. 351 minus 440. Okay. Negative 89, and then CV4 or CV for air. Joules per... he said just multiplied, I guess, so times 716.5 is the number I got? 63 something something something? No. Okay, so that's wrong. I don't know why it's wrong, but that's okay. Oh, wait. 1,000 would also not give me the right answer. I don't know. I don't know what it is. Oh my gosh, I've been streaming like 2 hours. Well, that's funny. Okay, one thing you know what? I think we're gonna finish off with this because I'm gonna pop out and like get some food and stuff. So I wanna talk like a little bit about like what I'm gonna be lecturing about. So like, I think the first one is gonna be on like fluid, like what is a fluid? Like fluid intro. And we'll talk about like defining a fluid. We're actually going to talk about defining a fluid, and then we're going to talk about like fluid properties that kind of come from that definition of a fluid. And then we're going to talk about describing fluids. And I think I kind of want to have the problems be like on these. So I was thinking like there could be, because I'll probably say like, here's the textbook that I used, like, will you do some problems from that? Or like, the problems will be from that. And also any that I like and want to share from my professor who made them. A lot of them are from the textbook though, if you cared to go look it up, but I don't. I don't actually use a solution. I haven't used a single solution manual for this class because he was like really harsh about it at the beginning, and I was like, okay, I won't do it. And then I feel like he expects people to actually use them now because he doesn't provide any solutions. I'm like, okay, dude, what the hell, man? I want to just know what I'm doing is right. I don't care who tells me, if you tell me or somebody else tells me. But I think, yeah, like choosing fluids for things, I think is like a good sort of design segue there, or like something about like how can fluids like do work or make work easier. Like I think maybe asking a question like if you want to measuring like air pressure. Oh, well, I guess you kind of have to know about air pressure to do that. But I could write a little intro on it. Measuring air pressure, what fluid to use. And why. And then also, like, we could talk about... Like, that's a very good example of, like, a fluid property, like, depending on what you want to use that for. Or, like... I think maybe also talking about, like, incompressibility, I guess. Or, like, I might also do intro to assumptions in this lecture. Kind of depends on how much I can get to. These assumptions might be in the next one. The second one was going to be about... I think I want to have it be about, like, viscosity. Viscosity and, like, shear. And so this would be like, no slip. Like, what is it? Like, deep dive? Like, differing fluid layer. Because I like that problem. I like if you have a different fluid layer. That's a cool one. And then, you know, like Newton's law of viscosity. What else? Newton's law of viscosity and like modeling. Modeling things. I think like having a modeling problem is a good one here. Modeling problem experiment, because like, oh, it's like, oh, you want to set up this experiment, like how would you do this viscometer? I think that's like a really good applied, because I think the thing about like applied problems is either like you want to do a design thing or you want to do an experimental thing. And I think experimental things are also in that range of stuff. But if you want to do a design problem with shear, you could talk about like how you might want to like reduce shear, or although the other one that's really good with this one is like block on incline. Such a good problem. This one I definitely want to have available. Because it's just like a dynamics problem, which is really good. It's a really, really good problem. And then like for design, so this is like the design one, and then like well, that could also be an experimental one. 3 is pressure, all about pressure. So we start with like submerged. I don't know how long the lectures would be. They might be closer to 2 hours, but I think I would rather do some of this stuff like as a continued story. Although also I mean, you can do the proof for pressure fairly quickly. There's some stuff that definitely takes longer where I'm like, I listen to a lecture, I'm like, yeah, I don't really think you can put more stuff in this, but like, or planar, or pressure, flat, and then curved. But like, for these two, I really think like this is a thing you gotta do together. I think it would just make more sense. Although, you know, like maybe like an 1.5-hour lecture is a better time frame for something like this. I'll say like proof, and then flat and curved. And then we can talk about buoyancy. I probably won't talk about stability. And stability mention, but when you start talking about pressure, talking about design is like, there's so many good things. Like I would say like design, submersible, like wall thickness, and material choice. So that would add like, you know, some stress analysis in there. That's like a really fun one. Or you could, you know, design a, what's the word? Like a pressure vessel? Like a tank. Which is also sort of the same. They're kind of the same thing, but like the opposite problem. And then also with pressure, you could do buoyancy design, like so. You could do like whole design. That would be like stability and buoyancy. So like knowing that like a buoyancy is based off of like the water displaced, and like how do you you know, increase that or decrease that based off of the mass. Like I really want to have like an emphasis on, or like a design emphasis on sort of like contrasting variables, or like, so you can like graph stuff and you can kind of see like, you know, oh, like this has like a relationship like this, or graphs and analysis. So like in this one, like it would be either like I give a material or maybe I give a thickness, and there are a couple material choices. And it could be fun. I could make them like fake materials. That'd be kind of fun. It doesn't have to just be like 10 to 80 steel. Which I know what it is now, 1080 steel. 1080 is like not really something people use, but like 1040 people use. And 20? Question mark? Yeah, okay, so pressure, I'm probably forgetting some stuff. I'll have to like go back and when I'm like making the actual lectures and stuff, do more. And then I think it's control volume. And really, you only kind of need one. So like the idea also is like that the lectures are, they're sort of standalone, like there aren't problems that you solve in the lectures, it's just the theory. And then there's like, I might make separate videos on solving the problems, or I might just say like, okay, here's some streams of me doing like other unrelated problems, which are the streams which is happening right now. So like Reynolds proof, or I guess system explanation, systems versus CVs, and then we talk about Reynolds proof, which is you could do pretty quick. And then we talk about different I guess I should probably talk about intrinsic and extrinsic first. Yeah, that would be smart. Intrinsic, extrinsic properties. Trins properties. And then we talk about Reynolds, and then we talk about const mass. Okay, maybe we can't do all these. Linear momentum. Well, I mean, it's not super hard. You kind of just need to see problems done. Angular momentum, also not hard. Okay, this might actually need to be 2. Maybe. Or it might just need to be 2 hours. And then thermo. Because I want to talk about control volume choice. I think we do the Reynolds proof, we do conservation of mass, then we take a break to talk about control volume choice. No, before we do conservation of mass, we talk about control volume choice. It's not a super long topic, but I think it's important before getting into that to start thinking about that. And also slash chord sys choice. Oh, I like how I never really even talked about control volumes. Well, this is kind of that. I mean, I guess I could talk about CV choice in there. Would that be smart? No, I think right before we start doing it, it would be good to do that. Okay, control volume, that's all good. And then first thermo is like longer. This you need to talk about, like, I mean, there's more stuff to talk about there. Might be 2. And then diff analysis, which I haven't even done yet. That's gonna probably be something like for it. Navigator 6. And that yeah. And then probably what is it called? Dimensional analysis. And then pipe flow analysis. And then for control volume, there's not a lot of like fun, or I mean, there's some fun design things you can do, I guess. Just like any problem, make variables variable. Lol. Right? Because you'll just do the problem and then you'll be like, well, what if this thickness was different, or what if this other thing was, what if this density was different? Like, you know, could I get it to go faster? Do I want it to go faster? Those kind of things. I think that's good. And then I also have been thinking of doing like this class, like a combined class called like designing with stress, or designing for stress, which would be like, it would be like stress intro, stress strain in beams, like axial. Oh well, stress strain in beams, this would be like axial, torsion, what other ones are there? I already forget. Axial torsion, you do, wait, axial loading torsion, oh, shear, like, bending diagrams. Bending diagrams, yeah, that for 2 weeks. And then, like, I mean, combined loading. No, I think there'd be another one on combined loading. Oh, wait, we have to talk about, wait, shear. Stress strain in beams, normal. And the second one would be shear. So like axial origin. And then combined loading. So basically turning a 10-week course into 3 videos, which like doesn't, it sounds crazy, but like is not actually that bad. It's not a lot, like you're not gonna get like the exact theory, but it's more about like knowing about it and like doing some of the back of the cuff calculation stuff. Combined loading, and then you would do like principal stresses, or transformations and principal. And maximum stress strains. Because this is also a very simple topic. And this is like also, so this would be like, so stress matrix. Well, I mean, we talked about stress matrix at the beginning. Probably you'd have to start with like a what is stress here and what is strain, which, you know, honestly isn't that hard to explain. What is stress / strain? And then, yeah, transform, so like more on stress matrix, I guess. And then like change of basis. I don't know what this, I wish wouldn't be a whole episode, but I mean, you know, it could be like a small episode. Change of basis. And then, yeah, I got like a more circle. Brief, because you're never going to use it. You're going to do matrices. With matrices. And then, yeah, that's pretty much all that. And then, like, stuff that I haven't done yet. So, like, stress concentrators. This is, like... This is... CE... Wait, sorry. This is CE 204. This is CE 207. It's like, okay, there's other things you can do. You can do, like, the... We're gonna do... differential equations to describe beam loading, but like you don't really, you're not gonna, you know, necessarily use that. And then this would be like stress concentrators and other sort of like design for strength and stiff stuff, which I haven't done yet. So I mean, I'm assuming there's other things in there, but like that'd be a fun little like, oh, you want to learn how to like, you know, use strength, stress and strain in your design stuff. It's not really that hard. It's just like there's the first chunk of that is a lot harder than the other stuff. But if you don't go into the theory and poorly take like, you know, an hour and a half to explain the theory badly and then, you know, end up not even teaching it, then it becomes a lot shorter. Anyway, I think I'm gonna wrap up now. Thanks everybody for hanging out. I think that was pretty good. I'm gonna check out that Shapes game for sure. I definitely want to play that a little bit. I'll be back maybe tomorrow. I don't know, or maybe not. Probably. Either that or Wednesday. I don't really want to stream Tuesdays. It's because it kind of throws my schedule off. So, yeah, we'll be back then. Thanks for hanging out, everybody. See you later. Bye.